everyone. So, in this lecture we are going to talk about the MSCR analysis using Matlab. We all know what MSCR is. It is multiple stress creep and recovery test, which is mostly used for modified bitumen to capture its elastic recovery properties, right. So, we know how the test is also performed. I will do a small recap of the test procedure before beginning to analyze the data. So, in this lecture we will see how to import MSCR data into Matlab and how to calculate the parameters which are specified in ASTM D7405. So, they ask us to calculate percentage recovery at two different stress levels, non-recoverable creep compliance at again two different stress levels, and the percentage recovery difference between the two stress levels and the non-recoverable creep compliance difference between the two stress levels. So, these are some of the parameters which are specified in ASTM D7405. So, in this lecture we will see how to import the data in Matlab and calculate all these parameters using Matlab. So, this is the outline. We will first talk about what is an MSCR test, and then we will see how to plot the data which we get from an MSCR test, and then we will see what are the parameters that are required to be calculated, how to calculate percentage recovery, and then how to calculate non-recoverable creep compliance. The first one is what is an MSCR test. So, what is an MSCR test? We can see here. So, an MSCR test is a multiple stress creep and recovery. It is a multiple stress creep and recovery test. We perform the test at two different stress levels, 0.1 kPa and 3.2 kPa, and then we know that we apply a loading for 1 second and we measure the recovery for 9 seconds. So, we have a loading which is applied for 1 second and the recovery is measured for 9 seconds. We have 10 cycles at 0.1 kPa and we have 10 cycles at 3.2 kPa. So, this is a schematic of the MSCR test. Now, using this data, how do for this experiment what we get is the strain values, how the strain. So, they call it as shear strain since we do an oscillatory test. So, we will see how the strain varies as a function of time, right. So, this is how the experiment is done. Now, this is the data which is generated. So, we have done some trial in a laboratory and captured the MSCR data. So, previously when I showed you the amplitude sweep, you saw a number of variables which were listed here. Again you can modify that, you can specify what are the variables which you require to see. So, for this experiment we have collected only or we have imported only few variables. One is time, the other one is temperature, shear stress and then shear strain. And you can also see the units here. Time is given in seconds, temperature again degree Celsius, shear stress is kilopascal and shear strain is in percentage, right. And you can see here that every data point is collected for 0.1 second, because here you see 100.11, 100.21, 100.31. So, like that the data collection point is varied, right. So, we have collected data for every 0.1 second. So, for one cycle which is for 10 seconds, because we saw that we have 1 second loading and 9 seconds recovery. So, one cycle is for 10 seconds. So, here we will have 100 data points, right. So, this is the data which we have collected. What we are interested in the plot of shear strain, how the shear strain varies as a function of time, right. So, we will have some creep depending upon the material, we will have some recovery and then it will shoot up to the next strain level, some recovery, so that it will keep going on. So, this is what we are interested in. So, we have to extract these variables into Matlab. So, by this time you know how to read only these two variables into Matlab. So, like I mentioned in my previous lecture, you can see that we have added to clear the command window and the workspace, and then we have imported the data. So, data is XLS read of the particular file name along with the sheet number, and we have also extracted X data and Y data. So, it is data from 4 to end of the second column and Y data is 4 to end of the fifth column. So, here you can see second column is time which we want in our x axis, and fifth column is sixth column in fact is shear strain which we want in our y axis. But when you are importing, you can see that in data you will have only 5 columns because it has neglected this column which does not have any data. So, that is why we are seeing only 5 columns in our data which is shown here. The first 3 are not a number which has some information strings about the experiment, and the data starts here, right. So, I have added one more point. Generally in a multiple stress creep and recovery test, we will perform some pre-shearings, like we have 10 cycles in 0.1 kPa and 10 cycles in 3.2 kilopascal, that is what we have said, right. But the AASHTO code suggests us to do some 10 cycles as preconditioning cycles at 0.1 kilopascal. So, instead of the 10 cycles in this stress level, we will actually be doing 20 cycles. The first 10 will be taken as preconditioning and the next 10 is what the experimental data is. So, the strain corresponding to the recovery of the 10th preconditioning cycle will be the 0th point for the subsequent cycle. So, that data is not represented here and hence that data is added to this. I have done it manually. Generally when you collect data from DSR, you will get this by default. So, you have to take this as the initial value, because see, when we have our creep and recovery test, so this is the initial portion which will be the last data point corresponding to the recovery of the previous cycle. So, this would have been the previous cycle would have been recovering something like the previous cycle would have been recovering something like this. So, this will be the initial portion for the next cycle. So, this data point we need and that is shown here, right. So, this is for the creep and recovery data. We have to ignore all these things and read it from the fourth line. So, we have extracted and you can see here this is our x variable and this is our y variable. I can alternatively save this as time and this as strain. I can name it this way also, there is no problem because all of them are just variable names. So, you can see we have our y data also which is given here. Next is how to plot this data. So, the syntax for plotting is just give plot x comma y, right. So, which means that this one will be whatever be the name will be on the x axis and this one will be on the y axis, right. So, we have generated a plot x comma y and you can see that this is the data which is plotted, right. So, we have time which is given here, since we have not given any label it has not shown it, and here also we do not have any label, and you can see here that this is the first 10 cycles corresponding to 0.1 kilopascal, and these are the from here to here are the 10 cycles corresponding to 3.2 kilopascals, right. But here we can see that we are not even able to see the creep and recovery. On a first look you will see that it almost looks like a straight line. The reason is the scale, because the strains are substantially higher, again depending upon the material the scale will vary, for a higher stress level of 3.2 kilopascal compared to a lower stress level of 0.1 kilopascal. So, the magnitude of strain is also different, and that is why we are not able to see the creep and recovery part at 0.1 kilopascal, and that is why we have to use a log scale. So, here we define some attributes. So, you can just use this syntax for now. You give set GCA and then you put y scale within quotes and then you say log. If you want to change x scale, you just put x scale log. So, then the x scale will be automatically changed to a log scale, but since we want only the y scale to be changed into log scale, we have just given here y scale comma log, and then you can see that this will be changed into a log scale. You can see it here. Now, this is in the log scale, and then now the creep and recovery portion for 0.1 kilopascal is very evident, right. So, this is how you plot. If we have different materials, we can plot different plots on the same figure, and then we will be able to compare the creep and recovery or the strain levels for different materials. So, if you want to make that plot, let us say we have 3 sets of data x1 comma y1, x2 comma y2, x3 comma y3. So, then we first plot x1 comma y1, you specify, hold on, so that it will replot in the same plot, and then you give plot x2 comma y2, hold on, plot x3 comma y3. Then we will be able to get all the 3 plots in the same figure, and then we can compare across, right. So, this is possible, and then we want to change the label. So, if you want to add it in the code, you just say x label within braces, you put time in bracket seconds within single quotes. So, then the x label is now changed to time in seconds, and similarly you give y label within braces, we specify the name, right. So, then we will be able to see that the axis labels are also now generated. So, it is a plot of time versus shear strain, right. So, this is how we make plots using the data. Next, we start calculating some parameters using this particular data. So, the 2 parameters which we are going to see here are percentage recovery and non-recoverable creep compliance. Now, these are the parameters to be calculated based on the specification provided in ASTM D7405. So, we can see that we calculate the percentage recovery for 100 Pascal shear stress and 3200 Pascal shear stress, and the percentage difference in recovery. Similarly, JNR for 100 Pascal and 3200 Pascal shear stress and the percentage difference in JNR. So, this is a snapshot from a previous lectures in which I explained what an MSCR test is and what are the parameters to be calculated. So, the percentage recovery epsilon r is calculated as epsilon 1 minus epsilon 10 by epsilon 1. So, what are these variables epsilon 1 and epsilon 2? So, epsilon 1 is the total creep strain, that is from my 0th time to the end of 1 second. So, when I start the test, when 1 second of loading is completed, how much of strain is accumulated in the material. So, that is my epsilon 1. So, when we have to do this calculation, the last value of strain from the previous cycle will be epsilon 0 for the current cycle. So, like I previously explained, you have to take that into consideration, and then this strain at the end of 1 second loading can be taken as epsilon 1, and then epsilon 10 is nothing but the strain at the end of recovery. So, we allow the material to recover for 9 seconds. So, at the end of 9 second recovery, the strain which is accumulated in the material, right. So, this is epsilon 10. So, for the next cycle, this will be my epsilon 1, and so I have to take this as the baseline, and this will be epsilon 10. So, this is how we have to calculate these parameters when we are using the code. So, we have to be clear about these things. So, the first one what we look into is percent recovery. So, for the 10 cycles, so this is the snapshot from ASTM D7405. So, they have specified that for 10 cycles at a stress level of 0.1 kilopascal, we calculate percentage recovery like this, and for the 10 cycles at 3200 pascals or 3.2 kilopascal, we calculate the percent recovery using this formula. The formula remains the same. What they mean here is you have to calculate it separately for the two different stress levels. Now, let us see how to do that. So, this is the code which is written related to that. So, we have to create a loop to do that for all the 20 cycles. So, how do we read the data? Because in our data it started from point 0, which is the last point from the previous cycle, and then we will have 100 data points in a cycle. So, including this it will become 101 data point, and then we have the next 100 data points for the next cycle. This is cycle 1. So, this is 100 points for cycle 2. So, like that it keeps going on. So, it is a continuous data. Now, we have to separate that data to calculate your epsilon 0, epsilon c and then epsilon r. So, epsilon 0 will be the time in which I start, epsilon c will be this strain, and then it starts recovering. So, this is epsilon r, right. So, we need to identify this for each and every cycle, right. So, a loop is created. So, I have used the same names to avoid confusion, and whenever I need to call these variables in future, it will be helpful. So, I have epsilon 0, epsilon c and epsilon r. So, what do I mean by a loop? So, when it has to do the same function a number of times, then we create a loop, and the loop here is defined using another variable j. So, when j varies from 1 to 20, so this will be executed 20 times. So, j will vary 1, 2, 3 like that from 1 to 20. So, when j is varying from 1 to 20, how do we get it? So, epsilon 0 is nothing but y, because y is our strain value, right. So, y of j minus 1 into 100 plus 1, I have defined it this way. Let us see why it is defined in this manner. I will show it with an example, then you will be able to understand clearly. So, epsilon c I have explained as y of j minus 1 into 100 plus 11, and y is epsilon r is y of j minus 1 into 100 plus 101. Now, let us take the first cycle. So, for the first cycle j will be equal to 1, right. So, epsilon 0 is nothing but y of j minus 1 is 1 minus 1, which is nothing but 0, 0 into 100 will be 0, right, plus 1. So, the first data point which is there for y. So, in the Excel sheet we saw that we have added one point which is the information related to the last data point of the previous cycle. So, that is the first point here, which is epsilon 0, the starting point for the next cycle. The next variable is epsilon c. This epsilon c is again y of j minus 1 into 100 plus 11. So, which is nothing but 1 minus 1 is 0 into 100 plus the 11th data point, right, because 0 is corresponding to the previous cycle, and we said we are collecting data for every 0.1 second. So, the 11th point will be the maximum point. Otherwise, if we do not have information related to the previous cycle, actually 10th data point should be the maximum point, right, because we said we are loading for 1 second, and since we are collecting data for every 0.1 second, we will be having 10 data points for this creep portion. But since that data point is included here, I have to make it as 11. So, which will correspond to this peak strain here. So, that is why it is given as y of 11, and epsilon r is y of again 0 plus 101, because we said we have 100 data points for every cycle plus the first data point. So, we have 101. So, this 101th point will be the epsilon r, right. So, we have calculated. So, this is how we read. So, when we go to the second cycle, right, we will see what happens. Now, j will be 2, right. So, epsilon 0 should be the 101th data point, because that is the last point of the previous cycle. So, you read here j will be 2, 2 minus 1 will be 1, 1 into 100, 100 plus 101. So, it will be y of 101, right. So, we have taken for the next cycle the last data point of the previous cycle, that becomes epsilon naught. Then epsilon c is nothing but 2 minus 1 is 1, 1 into 100 is 100, 100 plus 11. So, y of 111. Similarly, we will get epsilon r as y of, so it is 100 plus 101, which will become 201, right. So, like that we will calculate the points for each and every cycle. So, it will do this for all the 20 cycles, right. So, we will get epsilon naught, epsilon c and epsilon r separately for each and every cycle. So, here we can see the values are specified here. Epsilon naught is given here, epsilon c is given here and epsilon r is given here. So, now using these three things we have to calculate epsilon 1, which is nothing but epsilon c minus epsilon 0, and then we also have to calculate epsilon r, which is nothing but epsilon 10, which is nothing but epsilon r minus epsilon 0, and that is how we have defined it as. So, now we have to calculate these two parameters, and for that the code which is written here is epsilon c, this should be actually epsilon underscore 1 and this is epsilon underscore 10. So, this should be epsilon c minus epsilon 0 and this is epsilon r minus epsilon 0. But what we have done here is that we have 20 cycles, right. We have 20 cycles and we should have had actually 20 points for epsilon 0, 20 points for epsilon c and 20 points for epsilon r. But we can see here that for all these three parameters we are only getting one value. That is because we have defined this as numbers rather than an array, and what happens is every time the second cycle, see for first cycle it would have calculated an epsilon 0, right, some value, and when we go to the next cycle this value will be replaced by the value of the second cycle. So, it keeps replacing and what we get here corresponds to the 20th cycle, right. So, we should actually define this as an array so that we will get all the data points individually. So, how to do this? So, here we define them in the form of an array. So, this we say epsilon 1 comma j and this epsilon is epsilon 2 comma j. So, we say for every cycle we ask Matlab to calculate epsilon c, epsilon r and save that in a file called epsilon, where the first row will be the epsilon 1 value and the second row, this is row 1 and this is row 2 will be epsilon 10 value, right. So, then next time if it is replaced there will not be an issue because it is already saved here in this epsilon matrix, right. So, instead of using epsilon, so instead of defining epsilon underscore separately and epsilon 10 separately, if we do this in the same matrix we will be able to do all the subsequent calculations in an easy manner. So, that is the reason behind saving these two variables epsilon 1 and epsilon 2 in the same variable epsilon as two different rows, right. So, here we can see we have epsilon, the first one j will be replaced. So, the first cycle will be the first column, second cycle will be the second column. So, like that all the 20 values will be saved as different columns, and we will see get epsilon, as I mentioned earlier, row 1 will be epsilon 1 and row 2 will be epsilon 10, right. Now, let us see what is the output. So, when we run this we see that epsilon matrix is generated as a 20 by 20, 2 by 20, right. So, which has 2 rows and 20 columns. So, that is how we have specified it as, right. So, the first row will be epsilon 1, second row will be epsilon. So, this is row 1 epsilon 1, row 2 will be epsilon 10, and we have got it for all the 20 cycles at one shot. So, we can have a look at the data. This is the epsilon. We can see that after the 10th cycle the strains have increased substantially because the stress level has increased, right. So, you can see the difference in your epsilon 1 and epsilon 10 between 10th cycle and 11th cycle. Next we will start calculating the parameters. So, the first one is how to calculate percentage recovery. To calculate percentage recovery, we have written this code. So, first we will define what percentage recovery is. We will write it down here. So, a percentage recovery is epsilon 1 minus epsilon 10 by epsilon 1 into 100, right. So, this is how percentage recovery is defined. Now, we will calculate this simultaneously for all the 20 cycles. So, for your k, which is varying from 1 to 20, and this epsilon and this parameter percentage recovery is calculated as the third row to our epsilon matrix. So, this epsilon matrix is already defined. Row 1 is epsilon 1, row 2 is epsilon 10, row 3 will be percentage recovery, right. So, this epsilon 3 comma k is nothing but epsilon 1 minus epsilon 10, right. So, into 100 is specified here divided by epsilon 1, right. So, that is specified here. So, then we will get the third row as the percentage recovery, and here you can see the third row is calculated. We can see the percentage recovery till 10th cycle, again it is about 27% is recovered, whereas after the higher stress level is applied, only 7% of the strain is recovered. So, we will be able to get this information using percentage recovery. The next parameter that we will calculate is average percentage recovery. So, we said we will calculate percentage recovery for all 10 cycles individually. So, for every cycle we will have one percentage recovery. So, for 0.1 kilopascal we will have 10 values, and here we will have 10 values. So, we need to average all these 10 values, and that is called as R100 or R3200 depending upon the shear stress level. So, how to calculate R100? So, this percentage recovery 100. So, I have named it that way for easy understanding. So, percent and so you should not write this with space, percent space recovery is not possible, but you can write it using an underscore. So, percent recovery for 100 Pascal shear stress is mean of epsilon 3 1 comma 10. So, what does this mean? So, the percentage recovery for 100 Pascal shear stress is the mean here will calculate the average value of what? The epsilon array for what? The third row and 1 to 10 column, because we said we are calculating it for 100, right. So, we have to take the first 10, the remaining 10 are for the 3200 Pascal shear stress. So, we calculate mean of epsilon of the third row for 1 to 10 columns. You can see here the percentage recovery value is displayed here. So, this is calculated for all the 10 cycles, and this is only one number because we are averaging all the 10 cycles. So, we get as a single number here. So, similarly, we can calculate R3200 also. So, this is nothing but percentage recovery at 3200 for the next 10 cycles. So, first we took the first 10 cycles, now we are going to take the next 10 cycles. So, it is mean epsilon 3 from 11 to 20, remaining things will remain the same. So, it is mean of epsilon third row from 11 to 20 columns. So, it will calculate the mean value, and you can see that the percentage recovery has reduced as we had seen earlier. So, this is how we calculate the percentage recovery for these two cases, the average percentage recovery which is specified as R100 and R3200. And we are also required to calculate R difference, which is percentage recovery at 100 minus percentage recovery at 3200 divided by percentage recovery at 100. So, which is nothing but R100 minus R3200 divided by R100 into 100. So, this is R difference. So, this you can straight away calculate because these are two numbers. So, you can specify it in the same manner. You have to note that here we are giving it as a loop because we have to calculate this individually for all the 20 columns, whereas here it is only one number. We are calculating one number here and we are calculating this for two different numbers. So, there is no need for to give a loop here, right. So, next is we can see the R difference value, it is about 75.45 percentage, right. So, this is the R difference value. Next we will calculate non-recoverable creep compliance. So, this JNR, right, it is said as JNR. So, this JNR is calculated separately for the two different stress levels as we have mentioned earlier. So, we calculate JNR as epsilon 10, right, divided by 100. So, that is how this is calculated and we kind of average it out to get the average non-recoverable creep compliance. So, this is for 100 Pascal shear stress and this is for 3200 Pascal shear stress, and we also calculate JNR difference, which is JNR at 3200 minus JNR at 100 divided by JNR at 100 into 100 as a percentage. So, how do we calculate this JNR? We calculate this JNR as another row to the same epsilon matrix what we have defined earlier, but we need to make a note here. The denominator is different for the two stress levels. For the first case it is divided by 3000, it is divided by 100, whereas for the second case it is divided by 3200. So, you can also do this in the same loop, but for the sake of simplicity I have split it into two different loops. So, in the first loop we calculate for the first 10 cycles. So, which is epsilon 4 comma k is epsilon 2 comma k, which is nothing but our epsilon 10 divided by 100. So, I have added these for the conversions, right, divided by 100. Similarly, from the 11th to 20th cycle the denominator here is 3200. So, we have calculated epsilon 10 into so, we have calculated epsilon 10 divided by 3200 for this case. So, we have the two JNR values, but both of them are calculated in the same fourth row. So, the calculation will be different, but both the numbers will be displayed in the fourth row. And then we also calculate JNR 100, which is nothing but mean of epsilon the fourth row 1 to 10. Similarly, JNR at 3200, which is mean of epsilon fourth row from 11 to 20, right. So, this is similar to what I have explained here for percentage recovery. And finally, we calculate JNR difference, which is JNR 100 minus JNR at 3200 divided by JNR at 100 into 100, right. So, now we have got all these things, we have saved all the information in one matrix which is epsilon. So, this has 4 rows. The first row will be epsilon 1, the second row will be epsilon 10, the third row will be percent recovery and the fourth row will be JNR, right. So, these are the 4 rows, you can see it is a 4 by 20 and then we have calculated some average values and then calculated the percentage difference. So, this JNR difference is, this should be other way around, JNR at 3200 minus JNR at 100 divided by JNR at 100, right. So, this is the JNR difference that we have calculated. Now, let us see what are the values which we have got. Ignore the JNR difference, we can consider JNR at 100 and JNR at 3200. So, based on the JNR value at 3200, the grades of binders are specified. So, we have seen this specification table also in our previous lectures. So, we see that for different traffic volume and speed conditions, the grades are specified using the JNR value. So, here we can see that standard or high case, the JNR value should be a maximum of 4 or maximum of 2, whereas for these two cases it is maximum of 0.5 and maximum of 1. Now, let us go back and look at our JNR at 3200. You have to see here that though we have calculated a number of parameters, this table is specified only based on JNR at 3.2. So, from here we can see that the JNR at 3200 is 1.6, right. So, when we come back to this table, we can see that these two cases should have a maximum of 1 only, but we have a value of 1.6. So, this can fall under this grade or this grade. So, the conclusion what we derive here is the given binder can be used for standard or high traffic conditions. So, this is how we analyze the standard multiple stress creep and recovery data to arrive at conclusions regarding the usability of this binder for different traffic conditions. So, this is the analysis which I have shown for a standard MSCR test. You can also do a number of customized tests. You can increase the load level to the loading from 1 second to 10 seconds, or we can do a lot of variations on this data, and for all such calculations we can use this methodology to calculate the different parameters.